Today we're going to do section 5.1. So first let's scan the book. Let's see, this is we've already scanned this page, so I will zoom in on the new part. Okay, that is should be good enough. Next, page 150 and 151. Let's see. Yeah, okay, that should be pretty good. Okay, and then a little closer on top. Okay, and then a little bit closer on the bottom. All right. Next, page 152 and page 153. Let's see, maybe like that. Let's see, about like that. Okay, and a little closer on top. And a bit closer on the bottom. Okay. And finally, page 154 to 155. Let's see. All right, there we go. That looks pretty good. And then a little closer on top. Okay, and a little closer on the bottom. All right, so that should do it. Today we are going to do chapter 5.1 on page 149. Now before I start, I want to mention, remind you what the word telescopic means when it comes to a sum like this. Okay, when you add up a sum like this, it will end up be equal to the last term and the first term, well, whatever, the last term, will be the last term. The last term subtracted by the first term. And the entire sum, okay? It doesn't matter if n is a million. The reason is because if you write this thing out, you get this deal, where x1, okay, start with k equal to 1, x1 minus x0, and then x2 minus x1, you notice x1 got subtracted out. And this continues to happen, okay? Each time you have xn minus 1, okay, xn minus 1, xn minus 2, the n minus 1 will get subtracted out. So all you got is the last term and the xn and the first term x0. This is called a telescopic something, sequence series something. And anyway, it just means that the result, you might have a big long bunch of stuff added, but at the end of the day, it subtracted itself out internally until you only have the head and the tail left. So remember, that's what the telescopic means. So having said that, we can start with chapter 5. Okay. First, let's please read the first introductory paragraph yourself about what the Stieltjes integral is for. And I will get to the definition. The definition is right now we're reviewing the Riemann integral that we learned in beginning calculus. That is, first we consider we'll have an interval from a to b. Okay, we'll subdivide it into a bunch of points where x0 is a and then xn is b, and then we'll cut it into pieces. Okay, where all the x's are different, right? One bigger than the next in order. Now, if we do that, then we get a bunch of intervals like this one. And then we define the word, what is that, delta? Yeah. Then we define delta is the maximum of the distance of these things, which are all positive here. So then as a result, we have, and then we'll choose a point psi of k that is within each interval. Okay, and psi of k is allowed to be the endpoint if necessary. And so then as a result, the Riemann integral is defined as such. Okay, where you put f is psi of k. Psi of k is inside some point inside or on the boundary of x from xk minus 1 to xk, and you do the sum, and then you add it up, and then you let you push delta to 0, which means n has to go to infinity for that to happen, being that delta is the maximum of these intervals. So even if the maximum of the distance interval of these low intervals go to 0, n has to go to infinity, and then all the stuff equal to the old Riemann integral, if the limit exists. Okay, it better exist, otherwise we're just babbling. And so assuming, so let's go to the next page. And next page, let's look at theorem A, where if f is continuous, okay, and on a closed interval, x goes from a to b inclusive of both endpoints, then the integral of f of x dx exists. Now this was now please read the next paragraph, short paragraph yourself, where you make certain comments. We're not going to prove this theorem A, so we're going to skip it and then move on. So please read the comments, and then we will continue with theorem B. Theorem B is the fundamental theorem of integral calculus, which is great memories from calculus 1, I believe. And so we have f of x is continuous, okay, and then it is the derivative of some big F, right? Some big F exists such that big F taking the derivative is equal to f of x. We're talking about everything is on the closed interval from a to b, and then if that is the case, the integral of small f from a to b is big FB minus big FA, right? That is very familiar, but we're gonna prove that here, okay? Offer an interesting little proof that's somewhat different from the proof that we learned in basic calculus. To do the proof, first we know that this limit exists, and if it exists, then it exists no matter how we take the limit, right? That is the definition on the previous page, where we have this thing. This thing, well, you have to choose the psi and choose whatever. But if it exists, that means it doesn't matter how you choose the psi. You will be able to calculate the limit, and the limit will be the same. Okay, you won't come up with a different limit depending on how you pick the psi or x, or how do you do subdivision. Doesn't matter how you do things, you will end up with the same answer. And that's the only way the limit can exist. If you end up with two different answers, then the limit doesn't exist. All right. So now, being that the limit exists, it doesn't matter how you choose psi of k for each one. And therefore, we're going to choose it specifically as that psi of k satisfies this equation right here. Now, this is, okay, let's look at the equation for a second. So we'll choose psi of k such that f x, the big F, okay, now we're talking about big F x k and big F x k minus 1 equals to some psi of k such that big F prime psi of k times the difference is equal to this. Now, how would you choose that? Well, you're going to choose it by the famous MVT, the mean value theorem, okay, which states that if things are differentiable or whatever, then you can pick for any difference of this kind, you can pick a point psi of k such that this equation exists. Okay, that's the good old MVT. And then if that is the case, then being that big F prime is equal to small f, that's given. Then this whole thing, then we have let me show you here. I wrote it down in my notes. I hope this is the right page. All right, so we have that. Then we can substitute this thing as the small f, okay? And then so when we do the summation of both sides, this big F and the other side is the small f. Big F is, by the telescopic principle that I just mentioned, is end up being FB minus FA, you know, the end minus the beginning. Because the whole thing, if you write it out, then you will see it. It's all the same deal. Now, being that this, and the other side, when you do the summation, that by definition is the integral, okay? By yeah, here's the definition of the integral. So when the summation as n goes to infinity is this one, and therefore we have finished the proof. That is, fb minus fa is indeed the Riemann integral. And all right, so that's that. Next, that's the proof of theorem B. Now, notice that this sum, okay, exists. We have established that this sum exists for any n. That is, it doesn't matter if n goes to infinity and if delta pushes to 0. Okay, everything stays the same, and therefore the limit does exist, and it equals to what it's supposed to equal to, which is this thing. Okay, and remember, delta is the maximum between the distances of x, any of these things. The xk minus xk minus 1, and that's the definition of delta from the previous page. So anyway, so that concludes the proof of theorem B. Now the rest of the book, okay, the rest of the page from here to here and all the way to the other side, all the way down to here until we go to this next section. Please read this yourself. Okay, it is a common description of the Stieltjes integral that is neat and stuff like that. So please read that yourself. Okay, and we're going to move on to the definitions on page 151. So please read this short paragraph yourself, and let's read, and then we'll read definition 1, which says the same thing as before. Okay, a subdivision delta of some interval will define it as a equal to x0, okay, which then goes up to x1, 2, all the way to xn, and xn is equal to b. The x's are not equal to each other, okay, they have to be strictly less than the next one, otherwise it wouldn't make any sense. So, but eventually you'll get to b, right? And then in a finite number of n's, and it might be a million, but eventually you'll get to b. So such a subdivision involves n plus 1 points, okay? It goes from x1 to xn plus x0, so n plus 1 points, dividing the interval into n chunks, right? N plus 1 points divide things into n pieces. That's called the tree planting problem or something like that from grade school. Anyway, so next, so now we got a bunch of intervals, okay? That's definition 1. And next, let's look at definition 2, where we define delta. Okay, delta is defined as the maximum of each little interval. Okay, and so then and it's called the norm delta. Okay, so we'll call it that. So that's which is the largest of the subinterval. Which one is the biggest? It's possible to find the largest because you have a finite number of intervals. Okay, eventually you can compare each one until you get to the end, right? You're gonna find the biggest one. That is, you take in computer science, what you do is if you have a finite number of stuff, right, and you want to figure out who's the biggest, then you take the first one, compare to the second one, see who's the biggest, and keep that one. And then you take what you kept, compare to the third one, and if the third one's bigger, then you throw away what you have and grab the third one. And you keep doing that, okay? Keep the one, that is, you compare to each one, and keep the one that's the bigger one. So once you go through your list, then you will have the biggest one, right? So that is why delta exists. That might seem obvious, but sometimes in math we need to be very clear, okay? That if something even exists, because if it doesn't exist, then we're just babbling nonsense. So that the delta, the norm, does exist. So next, let's look at definition 3. The Stieltjes integral is defined as such. Okay, now please pay attention to this definition carefully because we're going to be using this quite a bit in the homework section. Okay, and whenever you forget what it is, stare at this thing long enough until you see where it goes. Now, the Stieltjes interval is very similar to Riemann integral. The only difference is the alpha. There's an alpha here instead of just x. Otherwise, the definition is exactly the same, which means that the regular Riemann integral is just a special case of the Stieltjes integral. The Stieltjes integral just I don't know, put in a slight twist, okay, so that it includes more stuff. So it's not just x there. You can have all kinds of alpha x in the differential, right? So, but otherwise, it's the exact same thing. I mean, it looks exactly the same with alpha x replacing x. As a result, if you do, if it's just x, it's just a special case. So the Riemann integral is a special case of the Stieltjes integral. Okay, so then, so the rest of it is also comments on what happens when when things are changed, because this limit has a lot riding on it. That is, not just delta is going to 0, okay? N has to go to infinity, and then k, aside k, you could be picking any old thing, right? And that's anything between, as long as between k plus k minus xk minus 1 and xk. So, but either, so all that is. But as the norm goes to 0, all that stuff will be forced into proper behavior if the limit exists. All right, so that is what this is talking about. That situation is identical to what we just mentioned in the Riemann integral. Okay, the limit had better exist, but there are various situations that can happen that can vary, but all the varying changes nothing. Okay? Doesn't matter how you choose the psi or how you choose xk. This limit, everything had better go to the same thing. That is, as you force the limit as the limit of the norm go to 0, everything will converge into one value. And so that is what the rest of this paragraph is talking about. So please read that yourself. And then we'll go to the next page. Yeah, all the way up here, same thing. Okay, it gives a more detailed explanation of what all things. Your limit is forcing a lot of stuff to behave, and but if all things behave properly, then the limit exists. If any of the things cause the limit to not to exist, that is, if it goes to two different places or doesn't go anywhere at all, then your limit doesn't exist. It's that simple. So assuming the limit exists, then the Stieltjes integral is defined. Okay, and the other way is not defined, and we don't care about stuff that isn't defined. So please read that part yourself. And so now we're on page 152. So next, let's look at example A on page 152. The example A is now let's look at an example of this brand new Stieltjes integral that we just learned about. So the first thing we're gonna do is look at something weird. Okay, we're gonna define f and alpha the same way as some kind of a weird function. Yeah, what is it? A step function that is equal to 0 from 0 to 1, and then it jumps up to 1 from 1 to 2. Okay, one step. Now, if this is true, and we plug everything into the Stieltjes integral, then it is we find out that it's undefined. That is, you can't do the limit. So in other words, this is an example of where the Stieltjes interval cannot be defined for it. Now, why that is, please draw this out yourself, okay? And here's the explanation, although I believe you can understand this better just figuring out yourself than listening to me. Get this faster if you just if you just figure this out yourself right now, rather than listen to me try to explain it, because it's a very step functions are harder to explain than to understand, in my opinion. But anyway, so if you stare at it long enough, focus your attention on when x equal to 1, okay, because that's where the step happens. And everywhere else, stuff is just 0, because we're doing alpha xk minus alpha xk minus 1. But if around 1, however, it depends on how you pick the psi of k in this equation, okay? And psi of k could be, it could be either, can it be bigger than 1? No, I mean equal to 1. Let me fix that. Yeah, what I meant written here is depending on whether x of k is bigger than 1 or less than 1 or something, psi of k is either equal to 0 or 1, right? No, wait, what am I talking? Actually, that's correct. Never mind. I'm getting confused. So psi of k can be less than 1 or bigger than 1, depending on how you choose, maybe equal to 1, I don't know. So the point is the function, the f psi of k is going to be either 0 or 1, you see. And then you can, so the value of the limit, and when you try to nail it, it keeps jumping from 1 to 0, so as a result, the limit is not defined. And therefore, this is one of the examples where the Stieltjes integral cannot be defined because because there's a jump in there. Okay, yeah, and so that is that. The next example, example B, is fixing that problem in example A, where we'll define f at least and to not have a jump. And so f is just 1. Now, if f is just 1, then you can redo this problem, okay? And you will quickly notice that everything does focus just fine. And calculating it, you will find out that the value is just 1. And because the only value is during the jump, okay? So being the f didn't change, then the difference of x is 1. So then you multiply together, 1 times 1 is 1, and so on. So please do example B yourself. And that I believe you can figure it out faster than I can explain it properly. So then let's move down to theorem 1. Okay, so theorem 1 says that condition that where the limit exists. So okay. So now let's find a theorem to make sure that our Stieltjes integral actually exists. Okay, and the theorem 1 states that if you have a function, but first let's explain what the up arrow and the down arrow means in the paragraph. The up arrow means it's non-decreasing. Okay, it doesn't mean it's increasing, because increasing that means always implies that you're always going up, whereas non-decreasing just means it's okay to go level. Okay, you either go up or go level. As long as you're not decreasing, we'll use the up arrow to represent not decreasing and down arrow to represent not increasing. Although I would probably just call it increasing. That is, I would imagine increasing can mean well, increasing can mean if you're going level, that's okay. And well, although logically maybe that's missing a little bit. But in any case, the up arrow means non-decreasing. Okay, and so having said that, let's look at theorem 1. So if f is a continuous function and alpha is going up, non-decreasing, okay, and then the Stieltjes integral, as we have defined in the previous page, will exist, and that is theorem 1. Now, we're not going to prove theorem 1 yet. That will be done some other time. And we should let's go on to the next page, and we should mention that even though theorem 1 is defined for only the non-decreasing functions, if alpha points down, the same principle applies, that the integral exists as well. Okay, and that's the other situation. Now, so next let's look at example C. Now, example C, we have a function where f is a simple function, fx equal to x, and then alpha x equal to x squared. Still fairly simple, right? But it's not x. If it's x, then it would be back to the Riemann integral. So alpha x is x squared, and let's see how this works out. First, we know that being the x squared is a non-decreasing function, then this integral at least exists, so we know what, so then we can do something with it. So let's figure out what it is, okay? And we're going to figure out what it is the hard way. That is, we're going to go by the definition of the Stieltjes integral, which is on the previous page. Please look at it again, okay? The Stieltjes integral is defined as this thing, which is very similar to Riemann integral in the summation, well, as you force the difference. A difference of what? Oh, the difference of the subdivision into 0. Okay, then n is forced to infinity and stuff. So that is the definition. So please refer to this definition from time to time in this section, because you're going to need to do that in your homework. So that's the definition. Let's bear that in mind. And having said that, we are going to use that definition directly to calculate what this integral is. To do that, then we are going to, being that it doesn't matter which subdivision you use, we'll pick the easiest subdivision we can think of. So we're gonna choose integrals, sub-intervals all equal, okay, so it's all evenly divided. And then we'll pick psi of k equal to x of k, because psi of k is allowed to be on the endpoints, okay, in the interval including endpoints. So having said that, then we plug it into the Stieltjes integral formula, which I will show it to you again. Okay, it's this thing right here. So bear carefully in mind this equation. Okay, with this in mind, let's plug it in, and we get, of course, this thing right here, being that we are doing the even interval. All the subdivisions are the same. So each interval is 1 over n, right? So then the xk becomes k over n, and so on. So we plug it in right here. Now, and then alpha x is x squared. So we plug that in and write it out. It will become this thing as I have written out right here. And please do this yourself as well. So this is equal to that. I plug it in, and then doing the algebra in here. Quickly, you can do this in your head. K squared, k minus 1 squared. Once you do the subtraction, you get 2k minus 1, which is in the mean, and then plug it into the original equation where psi of, let's see, okay, continuing in the book, that is f of k over n is just k over n, because f is just f of x is equal to x. So we got this formula right here, and in a summation form. Now we're going to calculate this thing, okay, the hard way. That is, to do that, we need some formulas, which is given here. The sum of xk squared equals to this thing. This was mentioned in basic calculus. I think calculus 2, in the beginning of calculus 2 that it was taught. This is taught in middle school or something. And this is the area of the trapezoid, basically. Well, if you don't remember this thing, it doesn't matter, because you're going to be proving it again in the homework. It was proved originally with mathematical induction, probably in pre-calculus or whenever it is that you learned mathematical induction. But again, we're going to do this again in the homework, okay? If you don't remember it, that's fine. And so anyway, that's that. For now, we'll just take it as is and plug it into this formula right here, okay, these two things, and we're gonna translate it into something like this. And the translation, let's see, yeah, after we multiply stuff out, let me see, I have it written down. So this thing equal to that sum, right? And when you multiply the k, there's a k in here. Yeah, the k is in here. You multiply it out, and then you have in other words, you have, I pulled out the n, because n is not in the summation. So n comes out, then you have the summation of these k squared minus k. So with a 2 here. And so once we plug in those two summation formulas I got here, and then as you let n goes to infinity, then there's an n cubed here, okay? Calculating the limit, then this one goes to 0, because there's only n squared on top, so it's going to 0. This one, we will calculate the limit of each one. And remember that from calculus 1, that to calculate the limit of a fraction of this kind, what you do is you divide the top and the bottom by n. So this becomes 2 plus 1 over n divided by 3. And then as n goes to infinity, it's just 2/3. Those things become 1. Okay, so eventually it becomes, and that's where it comes from. And that's that. So after all that work, then we have calculated that this integral, doing it the hard way, is end up being 2/3 is what this integral is. All right, so that's the end of this section. Let's do homework. Let me find the homework. Okay, so for homework, please do, which is we're now on page, what? Is this on 148? No, it is not. Let me fix this. So for homework, on page 153, please do problems 1 to 15 and then problem 18. Okay, and when you're done, I want to talk about them. So let's first talk about problem 1. In fact, problem 1 to 5 are all messing with step functions. Okay, so I'm not going to say too much about them. It's just a matter of you paying attention to the details and make sure there is something is happening. Here is problem 1. We have well, whatever. So the limit equals to, well, it should equal to f at the value of f at 1, being the f is continuous, and this thing has one jump. So generally speaking, it equals to the distance of the jump, which in this case is 1, times the value of f at that jump. So that is, so please stare this a little bit, and then it will make sense to you. And then, so next, let's look at problem 2. We have, let's see, problem 2 is, it has a jump at end point, right? It doesn't matter if the jump is at the end point. The way the definition goes, because f psi of k can be chosen at the end point, right? So then the answer is still the same. The limit, which is the integral, is the same as the jump times the value of f at the jump point, being the f is continuous. Okay, f doesn't care that alpha has a jump there. F doesn't have a jump, so f is doing just fine. So the answer is the value of f at the jump times the distance, the actual length, height of the jump. And problem 3, same thing. Okay, now the jump is at the other end point, but the result doesn't change. And as you can see, the answer at the back of the book, it does check out. Problem 4 is if the jump happens at an interior point, that changes nothing. Okay, the value is equal to f at the value of f at that point times whatever the jump is. And then problem 5 says if f has a jump, f is not continuous, then we got a problem, because at the jump the value of psi of k can change. It can be the value before or after, and the limit can't force it to be stable. Okay, it's permanently allowed to go either before or after, and therefore the limit does not exist, which is the same as example 8, by the way. That's what example 8 is showing, and that is problem 5. Next, let's look at problem 6. Now, problem 6 requires theorem 9, which is on page 173. Okay, and I should probably have told you about that before, but I forgot. So remember, this to prove this thing, you have to use the theorem that's 20 pages later or something like that, and that's okay, because you say, well, but we haven't learned it. Well, it's but the theorem doesn't require anything that you don't already know, so we can just use it and not worry about what it means. So problem 6 is that we are going to evaluate, calculate limits 3 by calculate example C by a different trick than what they did in there. Okay, and what we're going to do is apply the law of the mean, the MVT theorem. So let's do that. Now, and then of course we need to use theorem 9 on page 173. Anyway, so to do that, we have, so here is the definition. Okay, always go for the definition first, and then but that's copied with the premise in the example C, where the subinterval is evenly divided into n parts. Now, having said that, we apply MVT, which means that this difference is equal to sine prime of something, where psi of k is going to be somewhere in here. I think the endpoints are okay too. I don't include the endpoints here, but you could, I think. And no, I think MVT doesn't include endpoints. Yeah. Whatever the point, no, I guess it doesn't include endpoints because we're applying the MVT. So anyway, it doesn't matter if it's an endpoint or not. The point is, so we come to this equation. Okay, so the sum got reduced to this thing, which might come in handy. Now, to calculate this thing, we notice that there are two functions in here that we need to force it into. What happened to, divided by n. So the n is still being divided, okay? So now what the problem is, now we have functions that has two things. The first function has a thing in here that we have to choose, and then there's a different value in a separate function. So that's where with this theorem 9 on page 173 comes in handy, because that theorem says that if you have two functions in there, everything still works, the integral still exists the same way. And to make it work, then we'll let the alpha, we'll call it alpha 1, okay? Because of the alpha here, we'll let alpha 1, which is different from that alpha, equal to x, the identity function. And so then the d alpha 1 is just dx. That is, we're back to the Riemann integral. And then we'll define the difference, of course, of alpha 1 is 1 over n. That's for each k, as we defined before. So then inside the theorem 9, they have an f, right? And then and a g, where the eta k is that is, we'll let the side indicate what's the eta k as our side k. Now, fitting all that in the formula, that means that this integral exists and is equal to what we had before, okay? And then using theorem 9. So then this is just the Riemann integral. What is side? And the alpha prime x, being the alpha is x squared originally. I guess I don't even have that written down here, but it is, okay? Because we're doing example C again. So alpha is x squared, and I have it right here. F of x is just x in the example C. So we write it all in and evaluate it as a Riemann integral. So then we got the same answer as before. Now this is and this might be slightly confusing because all the alphas, and we're using a theorem from 20 pages from now. But if you look at it carefully and just give it some careful thought, it will all make sense. So that's problem 6. So next, let's talk about problem 7. Problem 7 is we're proving equation 4, the one that is in the example C. Okay, that is this thing right here. We're gonna prove the sum of k squared. We're not gonna do the other one because that one's way too simple. And but you can look up the proof of it, of course, if you want to refresh your memory exactly how that was done. But anyway, that is so let's do this one, okay? And we're gonna do it by induction. Now, the induction process is first we'll figure out n equal to 1, all right? And then it works. And the formula works. N equal to 2, the formula still works. And then assume that the formula works for n. Does it work for n plus 1? That's where the induction logic comes in. So then we have, so we need to prove that, assume that something is true, okay? And what are we assuming? Well, whatever. We're assuming one of these things, and we have to prove that the other one is true. That is, we have to prove equation 1 equals to equation 2. That's right. See, equation 1 is the k squared. Okay, this is the k plus 1 squared. Does it equal this thing plus n plus 1 does equal to well, in other words, does this let's see. No, this is k squared n plus 1. Let me think again. Did I get this right here? Well, whatever. The point is, this is what we're trying to prove, okay? We're up to n plus 1. That's the new formula that if induction works, this plus that, which is this, should equal to that. So the question is, does equation 1 equal to equation 2, which means we have to multiply this stuff out, which I did not bother doing, okay? I just typed it into the calculator, and it says that it is correct. This is problem 7. See, and this is the Symbol Labs algebra calculator. I have the link below the video. So then if you type this in, and then it says the solution is 0. And while I'm showing you this, I might as well show you problem 9, a similar situation, okay, where you type this in, the solution is again 0, but the calculator wasn't able to get to the end. It got here, which is obviously 0. And when I type this in there again, then it admits that it's 0. It got tired. It just stopped right here. Anyway, so the next problem 10, so that's problem 9, okay, 10, same thing. When you type in, we're going to be doing something similar. You have to do a bunch of multiplications. Look at that. A bunch of algebra, which it will also be 0. So when you get to that problem, that's where you can refer to this if necessary. And just, well, it's just a matter of typing it into the calculator. Okay, so that is problem 7. Next, problem 8. What are we doing in problem 8? We are, what? Give me a second here. Did I get the problems wrong? Never mind, they just look similar. They're not. Anyway, so problem 8, we have to prove this relationship by using this trick, okay? Here's a trick. So to do that, we have to, first we'll confirm, well, we're not confirming nothing. Anyway, here's the trick. So that's what we are going to do. And let's see. So to prove this, we have, see, first this is equal to that. And that equals to that. That can be multiplied out rather quickly if you remember the, well, you don't need to remember anything, okay? This is just the 2 power thing. So anyway, so when you take 1 minus 2, and then you divide by 3, it indeed does equal to k times k plus 1. So we're confirming what the book gave us. Okay, so having said that, then let's add it all up. What is it? If we add it all up, and I wrote it out here, as you notice that this, the first term, when k equals to 1, the subtraction, this part is 1 minus 1. So that part is 0. So the first thing is 0. Okay. The second thing is here, which gets subtracted in the next term. In the telescopic situation. Okay. The same story here. The stuff gets subtracted out. So the only thing that's left is the last term, which is here, and the first term, which is 0. So even that is gone. So the only thing that's left is here, which is what we're trying to prove, that the sum of k times k plus 1 is this particular formula. Okay. Yeah, so that's that. So next, let's look at problem 9. So problem 9, we, what is problem 9? Problem 9 says, prove the equation 4. We're redoing that equation 4 again, that we already did in problem 7, right? Yeah. So we're proving equation 4 by using exercise 8, what we just did, and some relationship. Okay, another trick. So the same, use a different trick to prove, problem 7. And that's problem 9. So we'll write it down. Okay, the sum squared equals to that minus that, right? That part is obvious. So we plug it in. What is this? This we just figured out is that thing. Okay, and then sum of k, we'll just figure we know this. Okay, sum of k is that thing, and it can also be proved by induction, of course. So then we do the subtraction, and as I've shown you a little earlier in the that a does equal to b, and that's for problem 9. Yeah. Okay. Let's see, next. Next, let's do problem 10, which I did it with a straightforward mathematical induction. Okay, by induction, and we pick n equal to 1, n equal to 2, verify it works, assume n is true, does n plus 1 equal to correct, and by the calculator, I showed that it was right. And I think I showed it to you earlier, right? That equation. If I didn't, you can plug it in yourself. It's a very simple case. I didn't want to bother doing this by hand. Of course, feel free to do it by hand yourself, of course. So next, let's go to problem 11. Problem 11 says we need to now find sum of k to the power 4th. And so far, we have found k to the power, the sum of k to the power up to 3, right? Problem 10, yeah, problem 10, 3. So let's crank out 4. And then and here's a hint. The hint is we're gonna write k as this particular thing, okay? If it's possible. So if that's possible, then we can use the same tricks as we do before, because this is a similar trick as problem 8. And so first, let's multiply this out, see what it looks like, and then set, if possible, set A, B, and C to be 0. If we can make that happen, then this equation will hold, okay, as long as this thing comes out. So I used the calculator and got this. Let me show you what the calculator said. This is the Wolfram calculator, the Wolfram Alpha. I have the link below. Okay, it has. I used the expand function, where I typed it in. This ABC. Is that all we have? ABC. Yeah, I guess so. It will just have A, B, and C. Yeah, I think I typed it. This is the whole thing. So once I typed it in, and then here's the expanding thing. Then I collected terms. Okay, I focus on this line, and then I collected all terms that has by the power. Okay, collected the terms and set things to be 0. So that thing from the calculator, I wrote down K4 and all the terms for K3, which is A plus 6, and all the rest of the stuff has to go to 0. So A will be -6 from here, and then for K2 I got that, and B ended up being -7 because we already know A. So and then the third term C ended up being -1. And to make sure that I got this right, then I plug this back into the calculator. Okay, and that's the next line. See, I plugged A, B, and C into the calculator, and to make sure this does work out, and it does equal to which one is it? I think let me see. Give me a second here. Let me see where I did it. Right, I got it right here. See, when I plugged in A, B, and C, then this whole thing ended up being K to the power 4th. All other terms disappeared. See, so then so those terms are all correct. And so next, let's and then now we're going to follow the pattern from problem 8. Now problem 8 pulled this trick, right? We have let's see, where is it? Okay, problem 8 says we're going to rewrite where's the trick? Something about, right, here's the trick. Where it says K times K plus 1 is equal to these three things minus the one below it, okay, and divided by 3. So we are going to guess that because of that, we are going to follow the pattern, and we are going to guess that when you have one more term, now we have K plus 1, then times K plus 2 equal to 1/4 of this stuff. This is just with one more term, but it's identical to what the hint on problem 8. Okay, and this is just a guess. Okay, we're hoping that this is true. Now, so that is that's the second term. Now, I should mention that the sum of k in this summation, sum of k, we already know that. Okay, that was given before. Okay, and then the k plus 1, we also did this previously in, I don't know, problem. What problem is that? Whatever. In the previous problem, we already did this. And then so now we just need this one, okay, and yeah, and this one. We need both of those. So that is what we're shooting for. This one that is pink color, which is right here. So this one does. So the question is, does this equal to this? Okay. If it does, then we can use the same trick and following the same pattern of telescopic, because the telescopic trick will work again because this follows the telescopic pattern, and then we have this situation following the telescopic pattern. So then we figured out what this summation is, the pink one, okay? And that does work because I got it in the calculator. Let me see. Okay, the next one is to prove that our guess, this is to guess that the telescopic formula works and following the pattern, so divide by 4. And when I typed it into the calculator, it does give 0. And of course, you can do this by hand too, but I don't want to do it by hand. And anyway, so they are, in other words, these two things are the same. Okay, so so these things, this does indeed equal to this, following the pattern, and therefore this does equal to that. So we got this one taken care of, and finally the very last one, also the longest one, but it looks follow the same pattern. So I'm gonna guess that this equal to 1/5. See, the fraction keeps increasing one at a time. 1/5 of this stuff right here. Okay, the same pattern with one more term, k plus 4 and k up here and k plus 3 up here. But I need to make sure this is true. Now you can do this by hand, but I am so not doing that by hand. And what's the next one? Yeah. Okay, so here's the next one that I typed into the calculator. I think all I did is just copy and paste just added stuff into this one. Okay, so this the difference, and then change the 4 to 5, that sort of thing. Just added a few things in instead of typing the whole thing again. And anyway, so I typed it in, and they are indeed the same. When you subtract these two equations, it is indeed equal to 0. How nice is that, right? Yeah, imagine people in the old days who didn't have this kind of calculator, and to do this problem, they have to do all that by hand. How long is that going to take? Or maybe you prefer doing that, nothing wrong with it, okay? If you prefer doing it so much, that's even better. So then either way, the whatever that color is, orange, is that orange? Well, whatever. Anyway, this does indeed equal to, well, this part indeed equal to that. Okay, so the summation will follow the telescopic principle. This thing that I'm not even going to write it out is indeed equals to 1/5 of whatever. And so the formula is getting longer, but the principle stays the same. So eventually, eventually we got all these formulas. We got a formula for that, and that. So we, when they sum up, okay, down here. So here's the summations. Each one has figured out. So now we need to add all these things up. That is this one, the n, okay, plus that one, and then plus this one, okay, that's 1/2. Divide by half, divide by 3, divide by 4, and divide by 5. Look how much stuff there is. Let's add it all up and then come up with some formula. So I did that by using the Wolfram calculator. That thing is super cool, right? And I got this answer right here, which proves to be correct. Well, the answer is not at the back of the book, but I was able to confirm that the answer is correct anyway. So let me show you, that is on the next page. So let me show you how I typed this whole thing into the calculator, and then it was able to give me the result. So that this thing is, give me a second here. So I typed the whole thing in here, okay, this entire summation and all the ends formulas, this one, and don't forget the ABCs here, okay, these all has to go in. If you forget it, it's not going to come out. So then, so I got all of that in here. Take a look, okay. I used the simplify function in Wolfram Alpha, and then as you can see, once I typed all that in, it simplified it like it says it did. And well, that's how I typed it in. So I want to show you exactly it's typed in, because that thing is pretty picky, okay? And so you have to type it in very carefully, otherwise you'll have a fit. And so anyway, I typed it in, and it is able to understand it. And then it says, here's the result. So that is the correct answer. And the reason I know that is not just because the calculator says so, okay? It's because I also Googled it. Here's the Google result, which I took a screenshot of right here. And you notice the Google result is identical to this thing. Look at how cool that is, right? And yeah, so which means, which means that my result is indeed correct, because I seriously doubt that me and the AI are both wrong in the exact same way. Now, the AI isn't always right. I mean, at least for now. And when I try to use the AI to find math answers, a lot of times it's correct, but once in a while it's wrong. And however, even when it's wrong, it's only wrong by a little bit. You know, it isn't like it's a little bit off from the right answer, but it's still pretty close to the right answer. So, but anyways, but right now the AI says the same thing I did, so that should be correct. Okay, it makes me feel reasonably confident that we got the right answer. So that's problem 11. So next, let's talk about problem 12. Now, problem 12 to 15, I'm not going to say too much about it because it's all about limits, okay? Here's the, well, I'll just show you the whole page here. It's all a matter of just doing some limits homework, which is, I guess is okay. Okay, first problem 12, yeah, you follow the definition and then, well, we just have to calculate this thing. Well, we know they exist because of, and well, for the same reason that I did before, that because x squared is in non-decreasing. And then we just crank this thing out. There is yeah, and then so that's 12. 13 is very similar, right? In fact, 13 we already know the part of the answer from example C. That's just part of example C and times 8 times. So we can pull that in 8 times the answer of example C. So we don't even have to work too hard. So that is that's the answer. And next is okay, that's dx squared, and then 14, the same idea, right? Anyway, yes, 14, the same thing. We have following example C. This is just 27 times the answer of example C, basically. So that is that's that. And then problem 15, also a similar situation. Then yeah, let's just do some limit calculation, and that the answer is 3/4, and that does check out to be correct. And finally, problem 18 is, let me find it. Problem 18 just asks if you have 2 functions, okay, that the only difference is that one of them has a jump at an endpoint. What would be the Stieltjes integral? How would they compare? Well, then I would think that the value will be the same, except that the one that has the jump will be equal to the one that doesn't have the jump plus the jump, right? Being that it includes the jump, and that is yeah, that is all I can think of to say about that, and that marks the end of this section.